Today's learning goal is to apply Newton's second law. Apply Newton's second law. Okay, so let's take a look at this example. It says a spooky spider mass equals 0.5 kilograms. This is a large mass for a spider, so probably this is a Halloween decoration. Spooky spider hangs from the ceiling. What is the tension in the string? Okay, so this is the situation that we're considering. We've got a hanging mass. It's being supported by a string. Okay, the first step to solving these types of problems is going to be to draw a free body diagram. Okay, so let's go ahead and draw a free body diagram for this situation. So we're going to represent the spider as a simple shape. So in this case, I'll just use like a rectangle to represent the spider. And we're going to draw all the forces acting on the spider. So there is the weight of the spider, the force of gravity pulling the spider down towards the center of the earth. And the spider is not falling. There's another force opposing this force of gravity. That is the force of the string holding the spider up. So we call that the tension. Next, we should specify our x and y directions. So I want most of these force vectors, as many as I can manage, to lie entirely along the x or y direction. So even though we have a choice of coordinate system, we're going to pick a coordinate system that coincides with the majority of our force vectors. So I'm going to keep the traditional sort of up and down for the y direction. That way tension and weight both point along the y direction. And then we'll have the x direction perpendicular to that. Just like that. Next, I'm going to ask myself, what is the acceleration of the spider in the x and y directions? So in this case, the spider is just hanging there. It's not accelerating, it's not speeding up or slowing down. So its acceleration is going to be 0 in both the x and y directions. Step 2 is going to be to make a table of the x and y components for each force that appears in the free body diagram. So we're going to be looking at a free body diagram to build this table of x and y components for each of the forces acting on the spider. Okay, so looking at our free body diagram, we've got two forces acting on the spider, the tension and the weight. So our table will have two rows. Let's take a look at the tension. The tension points completely along the y direction. So it's not pointing in the x direction at all. It has no component along the x direction. And its y component is the entire length of the vector, the entire magnitude of this vector. So we're going to write capital T for the y component of the tension. Next, I should check the sign on this tension component. So notice it's pointing along the positive y direction, so I should have a positive sign here in front of my tension. Next, let me look at the weight. The weight is pointing again along the y direction, but this time it's in the negative y direction. So its x component is 0, right? It's not pointing along the x direction at all. And its y component is negative, right? Because it points in the negative y direction, negative mg. Negative mg because mg is mass times the acceleration due to gravity here on Earth. That's how we calculate the weight. Mass times little g. Little g is positive 9.8 meters per second squared. Okay, now that we have our table, step 3 is going to be to apply Newton's second law. So we're going to add all of the forces in the x direction here in our table and set it equal to mass times acceleration in the x direction. That's Newton's second law in the x direction. And we're going to do the same thing for the forces acting in the y direction. The sum of the forces along the y direction are going to be equal to the mass of the spider times the acceleration of the spider in the y direction. Okay, so let me take a look at the table. I'm going to add the forces acting along the y direction. So this is 0 plus 0. 0 plus 0 is 0, equals the mass of the spider, m, times the acceleration along the x direction, which we said was 0. So mass times 0. Any number times 0 is 0. So here we got a very exciting result, 0 equals 0. Okay, not really anything exciting happening in the x direction. But let's take a look at the y direction. We've got tension and weight pointing along the y direction. So I'm going to add the components of the forces acting along the y direction. Tension plus negative mg, so plus negative mg is minus mg, and that's going to be equal to the mass of the spider, m, times the acceleration along the y direction, which we said was 0, because the spider's not speeding up or slowing down in the y direction, it's just hanging there. So times 0. And mass times 0 is 0, right? Because any number times 0 is 0. And then we, on the other side, we still have tension minus mg. Okay, so now step 4, let me solve for whatever it is that I'm looking for. So step 4 is going to be to solve. Okay, so in step 4, usually we're going to end up with some sort of system of equations. Here, it's easy because in the x direction, we don't have any forces acting along the x direction. So we really only have one equation to worry about. So I'm going to rewrite it. Tension minus mg equals 0. And now let me go ahead and substitute in whatever values were given to me in the question. So in the question, they tell me that the mass of the spider is 0.5 kilograms. So let me go ahead and substitute that in for the mass. We've got tension minus 0.5 kilograms times little g is the acceleration due to gravity here on Earth, which is a positive 9.8 meters per second squared. And half of 9.8 is 4.9. So tension minus 4.9 newtons equals 0. And then in order to solve for tension, I should add 4.9 to both sides. So we're going to get that tension is equal to 4.9 newtons, because newtons is the unit of force. So that's it. This is our answer. The tension is 4.9 newtons. Okay, let's take a look at another example. This one says, suppose you, with a mass of 65 kilograms, are standing on a force sensor in an elevator that is going up. Okay, so the elevator is rising. The readout on the sensor tells you that the normal force on you is 325 newtons. What is the elevator's acceleration? Okay, so once again, we're going to follow the same 4 steps, starting with the free body diagram. So see if you can draw the free body diagram. Pause the video now. Okay, let's see how you did. So imagine, right, that box represents the person that's standing inside of the elevator with a mass of 65 kilograms. The forces acting on this person standing in the elevator are going to be the force of gravity. So the force of gravity is pointing down. And the normal force, which is pointing up. Right, the normal force always points perpendicular to the surface, and we're going to assume that the floor of the elevator is level, like is usually the case inside of an elevator. So the normal force is going to be pointing perpendicular to that surface, the floor of the elevator, which is horizontal. So in this case, the normal force is vertical. So normal force pointing up, weight pointing down. Once again, we want to pick a coordinate system in which the majority of our force vectors are pointing directly along the x or y directions to make the problem easier to solve. So it makes sense to line up the normal force and the weight with the y direction, since traditionally that's what we use for representing up and down. And then the x direction is perpendicular to that. Next, we should ask ourselves, what are the accelerations? So what is the acceleration in the x direction? What is the acceleration in the y direction? So in the x direction, the acceleration is going to be 0. You're not speeding up or slowing down in the side-to-side direction because it's an elevator that moves up and down. And in the y direction, we're being asked to find the acceleration, so presumably there could be an acceleration. Maybe we find out that it's 0, but we don't know that, so we have to leave this as an unknown. I'll go ahead and try to make the table of the x and y components of the force. Look at your free body diagram and make a table of the x and y components of each of the forces that appear in the free body diagram. Pause the video now. So for the forces acting along the x direction, we've got no forces acting along the x direction. The normal force is pointing completely in the y direction, so it doesn't have an x component, and its y component is going to be positive and equal to the entire magnitude of the vector. For the weight is pointing along the y direction, so again, there's no x component to the weight, and its y component is going to be equal to negative little little g. Okay, because the weight is pointing in a negative y direction and its magnitude is mass times gravity, mass times little g. Remember, little g is positive 9.8 meters per second squared. Okay, and those are the only two forces that appear in our free body diagram, so we only have two rows in our table. Remember that we make our table looking at our free body diagram. So every step that follows the free body diagram is referring back to the previous step. That's how we are able to solve these problems. Okay, third step, we are going to apply Newton's second law. So we'll add the forces along the x direction, add the forces along the y direction, and set those equal to mass times acceleration in the x, mass times acceleration in the y. Okay, go ahead and set up your equations. Pause the video now, add the forces in the x and y direction, set it equal to mass times acceleration in x and y, and check your answer by resuming the video. Okay, let's see how you did. Okay, so let's take a look at the forces in the x direction. We've got 0 plus 0, which is 0, equals mass times acceleration in the x direction, which we said is 0. So 0 equals 0. Okay, nothing exciting happening in the x direction. For the y direction, we've got normal plus negative mg. That's the sum of the forces along the y direction. Normal plus negative mg. So normal plus negative mg is going to be equal to the mass of the person in the elevator times the acceleration of the person in the elevator along the y direction. Okay, you're doing a great job so far. Go ahead and pause the video and see if you can solve for the acceleration in the y direction using these equations that we set up in step 3. Pause the video now. Okay, great job. Take a look. Here's the solution. Check your work. Normal minus mass times gravity equals mass times the acceleration in the y direction. Okay, the normal force I don't know, that's what I'm looking for. M is the mass of the person, the mass of this object, right? We said that's 65 kilograms. Little g is positive 9.8. Again, M, the mass of the person, 65 kilograms. And the acceleration in the y direction, we don't know that. Hold on one second. So we do know the normal force. They told us in the problem. Let's go back and read it carefully. It says that the readout on the sensor tells you that the normal force on you is 325 newtons. So we actually have one more piece of information. Let's go ahead and add that. That's the normal force. 325 minus 65 times 9.8 comes out to 637 newtons. And then this equals 65 times acceleration in y. Okay, so let's go ahead and solve this. So 325 minus 637 divided by 65 is going to be equal to our acceleration in the y direction. So this comes out to negative 4.8. So go ahead and put that in the calculator and check. This comes out to negative 4.8 meters per second squared, which is the acceleration in the y direction. So we got a negative acceleration in y, which means that even though the elevator is rising, it's coming to a stop. So probably you've had this like feeling before, like when the elevator is coming to a stop at the top of its motion, toward the end of its motion, you feel you got a little bit lighter. This is the idea. We've got a negative acceleration here in this case. The elevator is slowing down, and so are you. Okay, great job.